working at MDH, she says, for 6 years. Actually, I couldn't believe that. Before that, Jane reminded us that she had worked for the MPCA for a couple of years, along with Sherry Croning, on the ambient groundwater program. So she comes to us with a lot of experience and insight into the kind of thing that she's going to be talking about today. In 2019, MDH received funding from the LCCMR and the Environmental Natural Resources Trust Fund to look at emerging contaminants, these unregulated contaminants in surface water, in drinking water sources and finished drinking water for over 600 contaminants, most of them without any kind of health-based guidance values. The sampling for this was completed in December of 2021, Jane says, and more recently, they've started sampling public water supplies for PFAS. With the goal of sampling 90% of customers served by community public water supplies by 2025. And she's going to be talking about these projects today. Jane is an environmental research scientist at the Department of Health. She manages primarily investigative projects related to CECs in drinking water. She has a Bachelor of Science degree in Geology and Human Health from the University of St. Thomas and a Master of Public Health in Environmental Health Science from the University of Minnesota. Jane, the floor is yours.
Thanks, Mark. Hi, everyone. I'm Jane Lambert, and I'm going to be talking about our Unregulated Contaminants Monitoring Project and Statewide PFAS monitoring at MDH. I'm going to go ahead and turn my video off while I'm presenting. Having a little trouble moving to the next slide. Not sure if there's a lag.
Sometimes it takes a little bit. Just hang with it. It might be lagging a little bit. It was before, I noticed, when you tried.
Yeah. Oh, there we go.
Here we go.
So the Unregulated Contaminants Monitoring Project, or UCMP as we call it, is an LCCMR project. And the goals of this, this work were to essentially to characterize the presence of a group of unregulated contaminants in both drinking water sources and their associated finished water samples, and also to identify screening approaches to help simplify future monitoring efforts of this type. This work is funded by the Environment and Natural Resources Trust Fund, and our hope is that the results of this project will help us in our efforts to assist public water systems statewide in the areas of source water protection, water treatment, development of health-based guidance values, and risk communication. So site selection for this project, we included approximately 80 vulnerable community public water systems. We had several different networks that we included in the study. So we looked at surface water systems, and then we also looked at groundwater systems that are split into two different networks. One are systems that are associated with potential impacts from wastewater, and the other group is systems that are associated with impacts from agriculture. So we looked at several different criteria in putting our site list together. We looked at past water quality data. So for our agriculture systems, we identified them by looking at past pesticide data, nitrate, veterinary pharmaceuticals, bovine bacteroides, different indicators of agriculture in drinking water where we had the data available. For our wastewater systems, we looked at past chloride results, chloride-bromide ratios, bacteria detections, nitrate again, and if we had any data on pharmaceuticals or artificial sweeteners and pathogens in drinking water. We also looked at land use in determining which public water systems to include in the study. So for our agriculture systems, we looked at the number and type of cultivated crops within the DWSMA, or drinking water supply management area. surrounding the wells. We also looked at number of feedlots. For our wastewater systems, we looked at the number of septic systems surrounding the wells, the age and location of wastewater treatment plants. We also took into account geologic sensitivity and vulnerability, and looked at areas that were sewered versus unsewered in helping select systems to include. We also considered broad geographic considerations. We wanted to have a pretty representative group of public water systems across the state that hit the main regions. And we also wanted a variety of geologic settings. So we assembled a technical advisory team to help guide the project. Mark was a member from MPCA. We also had members from MDA, MDH, and the USGS. The USGS were also our partners on this project, so they're heavily involved as well. And so in determining which parameters we wanted to actually look for, we looked at previous studies and Minnesota-specific detections, because we wanted to sample for things that might likely be impacting Minnesota drinking water specifically. And like Mark said, we ended up sampling for over 600 different contaminants, and most of them had no MCL and no existing health-based guidance values. We ended up going with several different labs in order to cover all of the schedules that we wanted to look for. So we used the MDH Public Health Lab, SGS Axis out of Canada, and the USGS National Water Quality Lab. Because we had several different networks in the study, we tailored the contaminants that we looked for to each network specifically. So for surface water systems, since they're the most vulnerable, we sampled for the full list of contaminants. So we sampled them for pharmaceuticals, pesticides, wastewater indicators, personal care products, alkyl phenols, benzotriazoles, hormones, PFAS, and illicit drugs. Our wastewater impacted systems, we sampled for a shorter list. So we looked for pharmaceuticals, wastewater indicators, and PFAS. And at our agriculture impacted systems, we sampled mainly just for pesticides. We did sample all of the systems for general chemistry parameters and took field measurements. And our surface water systems, due to the seasonal variability, we took 2 samples at those systems. One was in the late summer and another in the late fall. But our groundwater systems were each just sampled once. And every time we went to take a sample, we took a paired, raw, and finished water sample. We hired 2 sampling staff to complete the work on this project. So we have Ariana on the left and Natalia on the right. As you can imagine, with over 600 contaminants, there were quite a few bottles and vials and syringes that they had to work with at each system. So they took each sample together, and they began sampling in August of 2019 and completed sampling in November of 2019. And the sampling that I've been referring to thus far is considered our phase 1. So we did end up having some extra funding where we could go back and take some additional samples, but this is just referring to our phase 1 of sampling. So as I mentioned, we're still getting data back from our follow-up sampling that we've done. So we haven't done a full, comprehensive, robust data analysis at this point. But the next few graphics will show generally what we found in phase 1. So this graphic shows the different contaminant classes that were detected, and the size of the circle corresponds to how frequently it was detected. So the big orange dot in the middle is lithium, the inorganic compound, and that was detected in 100% of samples everywhere that we looked for it. We also had detected 8 benzotriazoles, 13 different PFAS, 39 wastewater indicators, 53 different pharmaceuticals, and 60 pesticides. So breaking this down further to the most frequently detected compounds, those that were detected in at least 20% of samples, we have 11 pesticides, 6 PFAS, 1 inorganic compound, again, that's lithium, 3 wastewater indicators, 2 pharmaceuticals, and 2 benzotriazoles. So looking at this by the different networks and comparing source and finished water, you can see that we had the most detections in raw surface water, and then we saw quite a reduction between the source and finished surface water, which makes sense because surface water systems have pretty robust filtration and treatment installed. When looking at our 2 groundwater systems, both agricultural and wastewater network, it's a little bit closer, and we actually had some more detections in the finished water than in the source water, but they're still pretty close. So this chart shows our top 10 most frequently detected contaminants, and they're color-coded based on the contaminant class that they belong to. So again, lithium is at the top, our most widely detected compound. And then we have quite a few pesticides in the light green color. PFBA was our most widely detected PFAS. And we have tribromomethane, which is a disinfection byproduct, and 2 benzotriazoles. So I'm going to go into a little bit more detail on the PFAS results from the UCMP study. So I'm sure, as most of you know, PFAS has been manufactured in the US since the 40s. It's extremely persistent in both the environment and the human body. It's found in food packaging, different commercial household products, water-resistant clothing, firefighting foams. And PFAS exposure is linked to low infant birth weights, cancer, hormone disruption, and other health effects. So in this study, we found by far PFBA was the most widely detected. And the other contaminants listed here, PFOA, PFBS, PFAS, and PFHXS were detected between 23 to 25% of samples. When looking at the total number of detections across public water systems, we had 34 of the 46 had at least 1 positive PFAS detection, so that's 74%. And splitting this out between groundwater and surface water systems, we had at least 1 PFAS detection in 63% of groundwater systems versus 94% of surface water systems. But we did sample about half as many surface water systems as groundwater systems, and we sampled the surface water systems twice, so had a greater chance of detecting at least 1 PFAS. So it's not exactly an equal comparison. So this splits out the PFAS detections by public water system. So the numbers at the bottom correspond to a different public water system. We didn't include names. So overall, we see pretty good agreement between the number of detections in source versus finished water at surface water systems. We have some cases where we have a detection in the source water, but not the finished water, or the finished water, but not the source water. But overall, we saw it was pretty close between the two. And we didn't sample the same parcel of water moving through the system. So we didn't calculate how long it would take the water to move from the intake through the treatment plant to the finished water sampling location. We just had our samplers sample at the intake, and then when they were finished, sample at the finished water tap. So just something to note that we didn't include that. We wanted to have just a general idea of what are we seeing at the intake and what are we seeing at the finished water sampling point. And another thing, no systems in this study actually had treatment installed to remove PFAS. So any PFAS removal is just incidental. So this is the same type of chart, just showing the difference between source and finished water for our groundwater systems. Again, we see pretty good agreement between the detections between source and finished water. Systems 59 and 63 on the right end of the graph, those systems didn't treat, so we only took a source sample there. So that's why it looks like we have really high detections in the source water and nothing in the finished. It's because we didn't have a comparison of a finished water sample. So again, this is the same chart, just showing the concentrations of PFAS. So our average concentration in source water is 22 nanograms per liter versus 20 nanograms per liter in finished water at surface water systems, so pretty close. And then the same chart for groundwater systems. We had an average concentration in source water of 44 nanograms per liter versus 23 in the finished water. Another note too is we did our best to isolate the source at the finished water sampling location, but it wasn't always possible due to the different system design. So sometimes the system will have several wells that they run to an entry point or finished water sampling location. And we sampled individual wells in this study. So we would try to have them, if we were only interested in one of the wells, we would ask them to only run that well through the treatment plant so that we could sample an isolated version of the raw water sample that we took directly from the well. And in most cases, we were able to do that, but sometimes just based on the individual system, they weren't able to isolate that source for us. So all in all, one of the purposes of sampling for PFAS in this study was to assess the potential hazard to human health, and we do that by comparing the detected concentrations of PFAS in finished water to our existing MDH drinking water guidance. And health risk for PFAS is calculated via a health risk index, or HRI, which is a cumulative measure of PFAS exposure. So it takes into account the multiple PFAS that are detected at a given system in a given sample. And so we did have one system that exceeded the HRI of 1. And we were able to work with them, and they put that well in emergency status. And so they're now serving water that's below the HRI. So getting into what we're calling phase 2 of UCMP, or our follow-up work that we were able to do with our extra funding that we had. It's a much smaller scale than the phase 1 work, but we were able to revisit our agricultural network, and we sampled for PFAS and for cyanazine and its degradates. We were interested, it was brought up on the technical advisory team the first time around, sampling for cyanazine degradates, but we weren't able to do it due to the lack of analytical capability at the time. So we were happy to be able to go back and collect those samples at our agricultural network this past year. In addition to revisiting the agricultural sites, we introduced a new network of non-vulnerable wells in order to compare to our wastewater and agriculture networks. So we sampled 30 wells. 15 of them were in comparable land use settings to our wastewater wells, and the other 15 are in comparable land use settings to our agricultural network. But these wells are considered geologically protected, where our phase 1 wells are considered geologically vulnerable. So we're hoping to see how much does that geologic protection make a difference when the land use is similar. So now that we have most of our data back from phase 2, we're starting to really dig into our data analysis on this project. And so our research questions are to assess the occurrence and distribution. What did we find at what levels and where in the state? And also to compare between some of the different groups that we looked at. So are we seeing a significant difference in number of detections and concentrations between groundwater and surface water, between source and finished water, between our agriculture and wastewater networks, and between our vulnerable and non-vulnerable geologic settings? We're also hoping to be able to say something about human health risk because most of the contaminants that we looked for don't have existing health guidance. It's hard to do, but we are working with our health risk assessment group at MDH to see what tools are available and what we could potentially provide and be able to say about that. We're also interested in doing a comparison with our general chemistry parameters that we collected. Those are samples that we regularly take at public water systems. So if we can say something about the risk of contamination from our general chemistry data and the associations between the other contaminants that we looked at, that's another interesting piece. So switching gears a little bit to our statewide PFAS monitoring project. This project differs in a couple different ways. The UCMP project, as I mentioned, was based on sampling wells, and our statewide PFAS, we're sampling primarily finished water, and we're sampling all the finished water at a public water system that we visit. So the overarching goal guiding this project has been to sample community public water supplies that serve 90% of customers by 2025. We've been making really good progress on this goal, and it's likely that we will exceed that much earlier than 2025. So the ultimate goal is to eventually sample all community public water systems in the state for PFAS. Because PFAS isn't regulated, it's not required sampling, so public water systems have the option to say no when we approach them about sampling. So we likely won't ever get to 100%, but we're hoping to sample as many systems as we can. And of course, another goal of this is to determine if any systems have any health-based guidance value exceedances. So this is another project where we have phases, so I hope it's not too confusing. But phase 1 occurred roughly from June to September of 2021. We are working with contractors to complete the sampling for this project. So we worked with Wood. They went out and collected all the samples for us. And they sampled entry points or finished water at community public water systems. We also sampled a small subset of non-community systems, but it was primarily focused on community systems, and they sampled about 100 systems for us. The systems that we sampled in phase 1 are considered targeted. So we wanted to sample the systems that we thought might be at highest risk for PFAS exposure. So we chose systems that had wells that were within 1 mile of known sources of PFAS or detections of PFAS in the environment. And at this point, we've only sampled groundwater systems for the statewide PFAS sampling project. And we also focused our efforts on sampling geologically vulnerable drinking water sources. And this work was funded through a multi-purpose grant from EPA. It's actually a joint grant between MDH and MPCA, so we had quite a bit of collaboration in this project. So our site selection, a little bit more specifically, so we looked at different criteria to select our sites for this sampling project. We chose systems that had wells within 1 mile of spray irrigation sites or closed landfills that had PFAS detections. And those were provided to us by MPCA. We also looked at systems that are within close proximity to sites where AFFF has been used in the past. And we also received additional data from MPCA on basically all of the PFAS detections in EQUIS, mainly from the ambient groundwater monitoring program. And we also received some data from Dakota County's sampling program as well. So phase 2 is currently underway. It's likely going to wrap up in the next couple of months. There was some overlap between our phase 1 and phase 2 sampling. And again, we're working with contractors to complete this work. So for phase 2, we've been working with WSB to collect the samples. And they have only been collecting samples at community public water systems. They're sampling about 250 systems as a part of phase 2. And for phase 2, we broadened the scope a little bit. So the systems that we included weren't necessarily in close proximity to a detection or a source of PFAS, but we wanted to target systems that served larger populations and were located in urban areas. So most of the systems in phase 2 serve populations greater than 10,000, and they're also considered geologically vulnerable. And this project was funded by an additional EPA multi-purpose grant. So I pulled the data from this project as of last week. This is very preliminary. I didn't split this out by our different phases. This is just kind of a rough look at what we've received so far from this project. So pretty similar to what we saw in UCMP, PFBA has been by far the most widely detected PFAS, present in about 66% of samples. And the other contaminants listed are, we saw between 10 and 17% of samples. We did have a few other detections that I didn't include on the graph because they were only detected in like 1, 2, or 3 samples. And this is out of 591 samples so far that we have. And so overall, we have had 162 of 233 public water systems that had at least one PFAS detection. So that's 69% of public water systems. And at this point, we have sampled approximately 35% of community public water systems. And that's about 66% of the customers served toward our 90% goal. So far, we have had 3 systems that exceeded the HRI for PFAS, and that's a rate of 1.3%, so still pretty low. We did have 6 systems that have exceeded half of the HRI, or 0.5. So in those cases, we follow up with those systems just like we would if the HRI was above 1, and we complete quarterly sampling to get a quarterly running average to determine if the HRI is exceeded with those quarterly samples. So our next steps on this project are to wrap up our phase 2 sampling. We are hoping to initiate phase 3, which will likely happen this summer. And we plan to just have these ongoing projects and phases until we're able to reach our goal and essentially sample all community public water systems in the state. We'll be analyzing the data, completing our final reporting to EPA, and we'll be using the results to help set priorities for developing additional health-based guidance to inform future monitoring efforts. And in risk communication, we also are putting the data in what we're calling our PFAS dashboard. So this will be publicly available on our website. We're almost done putting it together. I think within the next month, it should be live. So all of this data will be shown on an interactive map. I have just a screenshot of what this is going to look like here. It's kind of hard to see the detail, but this is generally what it's going to look like. We have some different tabs at the top with information on the project and on PFAS, some information about the HRI and health-based guidance values, what those mean. We have a status tab that'll show all the systems in the state and whether they've been tested or not. And then we have a results tab where you can click on a system and it'll tell you, is the HRI exceeded, yes or no, what the range of their health risk index is, and then a list of any PFAS detections in a summarized format. So that's all I had for today. I'm happy to take any questions. See if I can.
Great, thank you, Jane. It looks like we've got one, and please feel free to either type your question into the chat, or you are certainly welcome to unmute yourself and go ahead and just ask Jane your question directly. We do have a question in the chat though, so I don't know if you're out of full screen mode or not yet, but do you know what the sources of the lithium detections might be? And also they are really looking forward to the PFAS testing dashboard.
Awesome, that's good to hear. I do not have a sense for much detail on the lithium data. I believe it's naturally occurring. So it may not be actually a contaminant source, but yeah, hoping to dig more into that as we do more data analysis.
Great. And we have another question here from Sarah, wondering if the PFAS detections in surface water are indicative of a current source or if they are due to runoff, etc.
Yeah, I think that's a good question. We get asked a lot about sources for PFAS, and it's tough to say. We haven't really gone into that depth of trying to track down the individual sources. But I think too, it's like with PFBA, we see it so frequently, it's tough to say, is it a source or is this just background in some cases?
Great. Do we have any more questions or comments?
Just as a follow-up comment to that, while we're waiting for more questions and comments from our audience here, Summer Streets just gave a presentation on the detection of PFAS chemicals in precipitation and in air. So that could explain, it could go a long ways to explain why, the ubiquity of these contaminants in the samples that you were finding, Jane. I think, the circle is starting to kind of close on some of that. It might not be just discrete sources. It might be PFAS that is coming from atmospheric distribution as well.
Right. Yeah, we detected it, and I think it was 70% of public water systems. So we're finding it more often than we're not finding it. But we do have some coordination between the agencies. There's a PFAS priority 1, 2, 3 group. So we meet with MPCA and we go through the systems that had elevated detections and try to have open communication that way. So if there potentially are sources that can be looked into, that we're communicating about those.
Great. And we do have a couple more questions that have popped up in the chat. So we've got a question here from Brennan. What was the general range of the laboratory method reporting levels for the different compounds?
I'd have to look, I don't know off the top of my head, but the detection limits are really low. So for our UCMP sampling, we used Axis for our PFAS samples. For our statewide testing, we're using the Public Health Lab EPA method 533. And we have had some JFlag data that we do include in our analysis. So results that are below the reporting limit but above the detection limit. And those are included on the dashboard as well. And we have a little footnote that denotes which ranges include JFlag data. But in general, the detection limits are very low.
Great, thank you. We've got another question. This one is, you touched on it a little bit, but maybe you want to expand on how the different agencies that are monitoring and looking into PFAS are coordinating. So this comment is suggesting that, you know, there's Department of Ag and MPCA monitor for CECs, pesticides, and others, and that maybe some kind of outward visible mapping or data to show the coordination that sounds like is probably happening. So if you want to maybe just elaborate a little bit more on that coordination.
Sure. Yeah, we've tried to coordinate as much as we can with the UCMP project. We had the technical advisory team, so we had Mark as a member. We had other members from MDA, USGS. So we tried to really include as many different voices as we could in determining what we want to sample for, how to select sites, what to do with the data. We wanted that to be a collaborative effort to make sure that we weren't just kind of thinking in our own silo about that. And then with the statewide monitoring, well, we have a few different ways that we've been collaborating. So on our phase 1 sampling, it was through a joint grant with MDH and MPCA. So I have bi-weekly meetings with Yodi at MPCA, and we share what we're finding, if anything has been exceeded, talk about sources, we share data back and forth. That PFAS priority 1, 2, 3 group that I mentioned, where we shared what we've found, what all the results are, who's being followed up with quarterly monitoring, what those results are. And then our statewide dashboard, we're hoping that will start more conversations and make our data more accessible so that others can see it and can follow up with us if there are specific questions.
Great. We have another question here from Justin on if there is a statewide map of the PFAS data and the concentrations detected, or a PFBA, for example.
So that's what we're hoping the PFAS dashboard will provide. It's not super customizable. As you look at the map, you can't like select different PFAS and see a map of just individual compounds. We were struggling with how to make the map accessible to people that don't have maybe a lot of technical experience, but want to see what PFAS looks like in their community. And so we tried to include enough information where people can get a snapshot and see a summary of the results and get a sense of, is their system exceeding limits or not, without including too much information where things just get lost for most people. So we're hoping that will provide a good sense of what's going on, but it's not, you can't customize like individual contaminants or drill down to that level of detail.
Okay, thank you. We have a question here from Karsten on what was the detection limit?
I guess they vary based on the different compounds, but I could, if you send me an email, I'd be happy to provide that. I'd have to look into it.
Okay. Yeah, so Karsten, your email's up on the screen right now, so grab it and then you can quick send her an email. We've got a question here from Scott about what is the mood at MDH about PFAS regulation in drinking water, commenting that PFAS is hard and expensive to treat, and I can't imagine the public being happy about any amount of PFAS in their drinking water. Seems like potentially a big problem for drinking water infrastructure in the future.
Yeah, I don't know if I'm the best person to speak to that, but I think generally we've just been waiting to hear what happens and working on our sampling as that continues. We think PFAS is something that's important to look for, and that we want to have a sense for what the state of PFAS is in Minnesota, so that if there are additional regulations, we can work with systems to assist them in meeting those standards, and we'll have a better sense of what that will look like after we complete this sampling program.
Great, and then we've got one last question or comment in the chat here from Sarah. One good thing about working to reduce PFAS in drinking water is that MDH Environmental Epidemiology Group has shown through biomonitoring studies that it works. People's PFAS serum levels decreased when PFAS is reduced in drinking water. So thank you, Sarah, for that comment. And while I was reading that, we did get one more comment. So I don't know if Jane, you wanted to comment on Sarah's comment, or if you want to move on to Justin's.
Well, thanks, Sarah, for your comment. And I think in addition to collaborating with other agencies, we've really tried to open up the collaboration within MDH as well. So our health risk assessment group now attends our monthly PFAS update meetings, and we're trying to have a high degree of communication within the agency as well. So we're aware of what health risk assessment is doing, and they're aware of what we're doing and how we can work together on those problems.
And then it looks like Justin followed up a little bit on the map. And so he is wondering if MDH has plans to have a more robust internal mapper that would allow analysis of each PFAS compound spatially throughout the state. I have a suspicion that PFBA background concentrations found in drinking water could vary spatially throughout the state and would visually tell an efficient and impactful story as more and more sites are evaluated as possible sources.
Sure. Yeah, at this point, we're really just trying to get our dashboard out the door. But I think it's a good starting point and something that we can definitely build on. It's a good place to start. And yeah, I could see in the future maybe making it a little bit more detailed, or including PFAS data from other groups, other sources. So definitely something that could be a possibility.
Great. Are there any more questions or comments or suggestions for Jane? Okay, wow, oh, nice job. So we are getting lots of thank yous and nice jobs. So I guess we will go ahead and wrap up here. We got one last one in before we wrap up. Has anyone declined to participate in the statewide monitoring project?
Yes. Yeah, we have had some systems decline. Usually it's smaller systems that might not have the bandwidth to be there when we need to. Sometimes in really small towns, it's like the person who does the water operating is also like the school bus driver, and it's tough to kind of match up sampling schedules, and or they don't they just decline for whatever reason. So we try to be upfront with our communications and let them know they do have the opportunity to say no. It's not required. We want them to understand that. But we try to explain the reasoning and the purpose and why it's important to test for PFAS. And by and large, most systems say yes, even the smaller systems. But there are always a handful that say no.
Yeah, that makes sense. I know I've run into some of these smaller communities where the wastewater operator is also the plow driver for the community. So, which is bonus for my work because I get to help them in 2 different areas of their jobs. But it can be tough because they have a lot on their plate. So that's understandable. Well, thank you so much for joining us today, for taking time out of your schedule to prepare this talk and to share your work with us. We're really appreciative for all of our presenters. You guys are really what make these sessions so great and so well attended, is that we have such great speakers. So thank you again for joining us.
Just as a reminder, we have another talk on February 24th from Rachel Cronhart. She's from the Shakopee Mdewakanton Sioux community. She's going to be talking about restoration of wetland complex as part of a mitigation effort from farm field to restored wetland. So make sure to tune in for that one as well. Jane, thanks so much for agreeing to tell us about the results of your studies. Really interesting stuff. Thanks much.
Yeah, no problem. And if anyone has additional questions, feel free to give me a call or send me an email.